In the early 1960s, NASA explored the impossible, a rocket powered not by chemical fuel but by a nuclear reactor. The NERVA Nuclear Thermal Rocket promised unprecedented thrust and efficiency, enough to carry humans beyond the moon and into deep space. Engineers imagined missions to Mars that could cut travel time by months. It was a dream of power, speed, and daring that seemed to come from the future. Yet building a nuclear-powered engine posed challenges unlike anything in rocketry before. Handling radiation, extreme heat, and complex fuels tested the limits of material science. Every test brought new insights and new risks. NERVA was a bold experiment that could have changed the course of space exploration forever. The concept of nuclear thermal propulsion emerged in the late 1950s, as engineers sought alternatives to chemical rockets. The goal was higher specific impulse and longer mission ranges. Nuclear fuel offered energy density unmatched by conventional propellants. NASA and the Atomic Energy Commission began collaborating to explore the technology. The first serious project was the rover program, led by Los Alamos National Laboratory. It focused on using uranium fuel elements to heat hydrogen gas. This hot hydrogen would then expand through a nozzle to produce thrust. It was a simple principle but an engineering nightmare in practice. Early experiments tested small reactors on the ground, measuring temperature limits, neutron flux, and structural integrity. Materials had to withstand over 2,500 degrees Fahrenheit without melting. Radiation shielding needed careful design to protect test personnel. The project pushed nuclear and aerospace engineering simultaneously. By 1961, NASA officially adopted the NERVA program, building on rover's progress. NERVA stood for Nuclear Engine for Rocket Vehicle Application. Its mission was to produce a flight-ready nuclear thermal rocket. Ambitious timelines envisioned manned Mars missions by the 1980s. The design relied on graphite-based fuel elements, impregnated with uranium. Hydrogen gas would flow through channels inside the fuel, heating to extreme temperatures. This process created thrust far more efficient than chemical rockets. The idea promised shorter travel times and lighter spacecraft. Engineers also focused on reliability. A nuclear engine failure could be catastrophic both in testing and in space. Extensive ground testing became a cornerstone of the program. Safety, performance, and endurance guided every development step. The NERVA engineers faced unprecedented engineering challenges. Fuel elements had to survive high temperatures and radiation simultaneously. Thermal expansion, hydrogen erosion, and structural creep were constant threats. Every component had to be meticulously designed and tested. The first full-scale NERVA engine, the NRX/EST, was completed in the mid-1960s. Standing over 10 feet tall, it dwarfed conventional chemical engines. Ground tests verified its thrust, stability, and cooling systems. Early successes showed that nuclear thermal propulsion could work in principle. Testing used remote-controlled facilities at Jackass Flats, Nevada. Operators monitored radiation, temperature, and thrust from miles away. Each firing was recorded in detail, providing critical data for engine refinement. Over dozens of tests, engineers gradually improved performance. The engines consistently achieved specific impulses around 850 to 900 seconds. This was nearly twice the efficiency of the best chemical rockets of the era. With this performance, missions to Mars could carry more payload or reach the destination faster. The promise of interplanetary travel seemed within reach. Engine failures were still common. Some fuel elements cracked, while others eroded under extreme hydrogen flow. Each failure informed redesigns, pushing material science further. The iterative approach slowly produced reliable hardware. By the late 1960s, NERVA had matured into a stable and powerful system. NASA's engineers envisioned integration into upper stages of interplanetary spacecraft. The program stood as a symbol of American ambition in the space race. Yet, geopolitical and budgetary pressures loomed large. With NERVA performing reliably on the ground, planners imagined manned missions to Mars. Chemical rockets would have required enormous fuel tanks and months of travel. Nuclear thermal engines could have transit time. Suddenly, crewed interplanetary travel felt possible. Engineers studied spacecraft designs using NERVA for upper stages. Large payloads could carry habitats, life support, and scientific equipment. Mission planners calculated reduced radiation exposure for astronauts due to shorter flights. The potential opened doors to serious human exploration. NERVA offered another advantage: throttle control. Unlike chemical engines, it could be adjusted in-flight to optimize trajectory. This allowed more precise orbital insertions and interplanetary maneuvers. NASA viewed this as a critical benefit for long missions. The program also explored dual-engine configurations for redundancy. Two engines could operate simultaneously for higher thrust or independently for efficiency. These ideas expanded mission flexibility. Engineers saw ways to reduce risk while maximizing capability. Political and financial realities began to interfere. Funding competition with the Apollo program limited NERVA's growth. Although technically ready, the engine was not prioritized for flight. Planners faced tough decisions about its deployment. International concerns about nuclear safety added complexity. Launching a nuclear reactor carried political and environmental risks. Public opposition grew louder even in the 1960s. These factors increasingly constrained NASA's options. Despite the obstacles, NERVA remained technically viable. Engineers proved that nuclear thermal propulsion was possible, efficient, and powerful. Its legacy persisted as a blueprint for future propulsion concepts. Humanity now had the knowledge to reach Mars faster than ever before. Ground testing exposed new engineering challenges. Radiation effects on surrounding equipment required constant mitigation. Hydrogen embrittlement weakened some components. Every firing brought fresh insights into materials science. Thermal stresses were extreme. Fuel elements expanded, contracted, and sometimes cracked under repeated cycles. Engineers developed new graphite composites to endure the heat. Iterative testing became the core of progress. Remote monitoring proved critical for safety. Operators relied on advanced sensors and cameras to observe engine behavior. Any anomaly could trigger a shutdown within milliseconds. This system ensured personnel were never exposed to radiation. Noise and vibration were also intense. The engines produced shock waves capable of shaking nearby test structures. Additional damping systems were installed to protect the facility. Engineers learned to manage every extreme environment safely. Fuel efficiency and performance improved with each iteration. Optimized hydrogen flow and nozzle designs raised specific impulse. Performance data exceeded initial expectations. The NERVA program proved nuclear rockets could be practical. Collaboration across NASA and the Atomic Energy Commission was crucial. Teams shared knowledge on nuclear physics, propulsion, and materials science. This partnership became a model for large-scale aerospace projects. The program thrived despite bureaucratic hurdles. By 1972, NERVA had completed over 20 successful full-scale tests. Each firing demonstrated long-duration operation and predictable thrust. Engineers documented every outcome meticulously. The program had proven its technical promise. Despite its success, NERVA was never flown in space. Budget cuts and changing priorities shifted NASA's focus to the Space Shuttle and unmanned probes. Political concerns over nuclear launches also played a role. The program was gradually phased out. Still, NERVA's technological impact was enormous. Its work informed modern nuclear propulsion studies and advanced materials research. Concepts developed for hydrogen cooling and fuel elements remain relevant today. Its influence persists in theoretical Mars mission planning. The program also shaped NASA's approach to high-risk experimentation. Engineers learned to test and iterate complex systems safely. Ground testing methodologies developed for NERVA influenced later aerospace projects. Lessons on extreme heat, radiation, and materials survived long after cancellation. Had it flown, NERVA could have cut human transit time to Mars nearly in half. Its efficiency and thrust were unmatched by chemical rockets. The vision of crewed interplanetary missions became more tangible. Its absence represents one of the greatest what-ifs in spaceflight history. Even in retirement, NERVA inspired future generations. University researchers and NASA engineers continue to study nuclear thermal propulsion. It remains a benchmark for any concept aiming to explore deep space. The program's boldness resonates decades later. Today, the NERVA program is remembered as a triumph of engineering courage. It pushed nuclear and rocket science to unprecedented limits. Its achievements remain a foundation for modern propulsion research. And though never flown, its potential still captivates the imagination. The story of the NERVA Nuclear Thermal Rocket is one of ambition, risk, and foresight. It represents what humanity can achieve when pushing boundaries. Its cancellation was a loss for deep space exploration, yet its legacy lives on. NERVA reminds us that the future often arrives in prototypes.